Well, thanks very much, Andy, and thank you to the organisers for this invitation to come and give you an update on where CyBOK has got to. So, as I think the presentation a number of years ago would have introduced the cybersecurity body of knowledge and what it was doing. Over the course of the years, there's been some additions to it, and today I'm going to be talking about a new knowledge area that's just come out earlier this year, informal methods for security. So I'll start off by just reminding you what's going on with CyBOK. So CyBOK is the cybersecurity body of knowledge. So it's essentially a coverage of the foundational knowledge in cybersecurity. So there's a big volume with 21 chapters in it, but also a whole host of surrounding material around that: podcasts, webinars, mappings, and so on that build on that body of knowledge. The aim of CyBOK is to focus on the foundational and generally recognised knowledge in cybersecurity, and it's been developed, by the community, by the academic community and the industrial community, in terms of bringing the knowledge together. And it's an international effort, although it's led from the UK. It's brought in expertise from all around the globe, and the intention is that it's not everything that's ever been done in cybersecurity, but it's the established foundation of the topic. So the idea is to put it on a firm foundation in the way that, for example, there's a software engineering body of knowledge, and other disciplines have established bodies of knowledge. And the intention of CyBOK is that it's a guide to the body of knowledge. So it's not an encyclopedia that contains it all, but it tells you where it all is. One of the key principles of it is that it's open and freely accessible. There's a website, you can go and download it. You don't have to pay for it. You don't even have to pay with your data. We don't ask for any information about who's downloading it, and that's deliberate to make it as widely and freely available as possible. And the process by which it's been developed is transparent, and there's a lot of involvement from the community. So the way that it's progressed as a project, it began actually way back in 2017 with scoping what should be in it in the first place, what counts as cybersecurity knowledge rather than other aspects of science. And after the scoping, then CyBOK 1.0 was developed, so the first edition, and that was released October 2019. Then in phase 3, there was some maintenance and evolution. So we continue to get input from the community and develop new areas. And then in July this year, 2021, the next edition came out, CyBOK 1.1. And we're now in phase 4, where it's growing and being rolled out more. So in terms of the input that we've had a huge number of experts, authors for each of the areas, a number of reviewers and advisors have been involved, including some from this community. And it's now got to over 1,000 pages. It's got over 2,000 references, and in terms of the comments that we've had from the wider community, over 1,600. So there's been excellent engagement from the wider community, and a number of invited talks and panels to get the word out, including this one. So CyBOK 1.1 is the one that came out in July 2021, introduced a new knowledge area, informal methods for security. So this was not in the original CyBOK, but actually formal methods appeared in a number of the other areas. So, for example, about authentication, authorization, accountability, or in software security or cryptography, hardware security, and so on. It appeared right through as a kind of cross-cutting topic, but it wasn't brought together under a single banner. So the idea was for CyBOK 1.1 that a separate chapter ought to be developed, and the proposal for bringing in this new knowledge area said that formal methods by itself is a well-established subject area. It does have a mature research community, so there is a body of knowledge there in its own right. Although it cuts across many of the other knowledge areas, it ought to be considered, in terms of what formal methods brings, in particular, to security. So where we came to was that we invited David Basin from ETH Zurich to put together the chapter on formal methods for security. So there was a proposal of what it should contain. That also went out to the community and had comments back. The strapline for the chapter would be verifying properties of critical systems. And in particular, formal methods is really an approach rather than a particular aspect of security. And it's an approach not only to security, but to development generally, and to reasoning about systems, software, hardware, etc. Where we wanted to focus on were particularly the application to security, because this is CyBOK. And so as overall, it fits into broadly two parts. There's the foundations and methods that talks about the underlying approaches that formal methods brings, and that focuses on specification, how you describe what should be, how you describe the kind of properties, requirements that you want, and verification, how you show that actually systems and components meet those requirements. So it focused on the foundations and methods generally, and then looked at their application in particular areas, right up and down the system stack. So we looked at hardware briefly, a big section on protocols and on software and systems, and then finished with configurations. So in one slide, this is really what the coverage of the new knowledge area and formal methods for security is about. So the section headings are listed here, and I'm just going to give an introduction to each of these areas. The chapter itself can be downloaded from the CyBOK website, and really the idea here is to just give you a flavour of what's covered in there, and to motivate you to go and read the chapter itself. The chapter is about 40 pages, and then plus references, etc. So it's a nice read. So I'm just looking to give you an overview of what it covers. So it actually goes to some effort to introduce and motivate what it's about, what formal methods is about, and for security. And as I said, it's about methods and tools for reasoning rigorously about systems and about their components. And the emphasis is on a firm mathematical basis. So using discrete maths, using logic, using whatever mathematical structures and ideas actually enable you to do this reasoning, so that you can make predictions about how systems ought to behave, and you can prove that they meet the requirements that they should have. So you would have a model, a mathematical model in your head, or written down, of what a system is, how it should behave, and the idea is that is a model, a representation of the system. The things that you prove about the model need to be true in the real system. The formal methods is there's a lot of effort that needs to go into doing these proofs, so it's particularly attractive for critical systems. You wouldn't use it for all software, but where systems are critical and it's vital that to get them right, then that's where formal methods really comes into play. And security is certainly one of the areas that is critical. So the focus is on modeling and proof, and this is true for formal methods generally, but with respect to security, there are particular aspects that come into play when we're looking at security. And one of the key aspects around security is the idea that we're operating in an adversarial environment. So we have some kind of adversary or attacker that is trying to undermine the system. So as well as having our model of the system itself, we also have to worry about what could an adversary do? What kind of attacks do we need to worry about? And then we'll also talk about what kind of security properties the system should satisfy. So we would include all of these aspects in a model. So for example, we might want to reason about whether information on a disk is secure or not. Well, that might be secure against a network adversary who can only access through the network, but not an adversary with physical access to the disks. So typically, modeling and proof would be with respect to a particular kind of adversary. Sometimes the adversary of property is not made explicit, and we're concerned about what we might also think of as safety properties, just the absence of certain classes of bugs. So we've heard earlier talk about things like buffer overflows or memory safety. There may not be an explicit attacker, but if these bugs are present, then generically they may allow an attacker to exploit them and do some malicious behavior. So sometimes the attacker is left implicit. We're just looking at particular kinds of properties. The scope is very wide in terms of how it applies to cybersecurity. So you can go right down to the hardware level. A lot of work is done on software. We can look at systems. We can look at design. So at a more abstract level of a system, how a system behaves, and also look at down at the code level. So formal methods looks at different levels of abstraction. And we can look at some very lightweight properties that we kind of almost don't even notice the checking being done, like type correctness, or can focus more deeply on more specific properties. And then it also covers a number of different approaches. So when we're doing these verification proofs, there may be interactive ways of supporting you to do like a mathematical proof, and there are also automatic ways of doing such proofs. So of course, there's a very strong overlap with formal methods as it's generally used for correctness, but there's new challenges for security, like this focus on the adversary, and so on. So in terms of motivation, one of the main motivations for formal methods is to do proof. It's been found, particularly with respect to security, that adversaries are not typical users. If there is a bug, then the chances are that they will find it. We all know about zero-day attacks and so on. So we have to, if we want to be confident that there are not particular kinds of vulnerabilities, we need to do more than just penetrate and patch, if you like, and try and recover from attacks. And generally speaking, we're looking at trying to progress from an art to a science in terms of development. Of course, there are limitations, and when I saw in the opening talk, I saw Paul's mallet. That made me think of this slide, where the system model, you have to worry about whether it accurately captures the requirements, and actually, are there other attacks that we haven't thought of with respect to the adversary? So here we may have a house that we've established, all the locks on the windows and the doors are absolutely secure, and there's no way that the access could be gained through windows and doors, but actually the attacker may have a completely different way in. So it's always going to be with respect to particular classes of attacks, and we have to consider whether these things are appropriate. And then, in practice, most security questions are undecidable, so we have to approximate as well, and or do manual proofs and those kind of things. So in terms of the methods and tools and foundations that are covered, there is no canonical best method. It depends what your particular problem is. So what the chapter does is introduce a whole range of different methods. It's not saying which one is best, because actually different ones are appropriate for different kinds of situations. So you may have when you're doing specification, you may have an ideal description of how your system should behave, or you may use logics to capture them. And for verification, there are automatic tools, and there are interactive theorem proving tools that can be used. And these tools are now at a mature level of where they can be applied for many real world analysis problems. And that's relatively recent that they're being applied really powerfully for difficult problems and doing proofs about real world systems. So at the foundational level, we can think of, for example, trace properties, system semantics given by sets of traces, and system properties also capture particular requirements. So, for example, here's an example using a temporal logic, and this one says that it's always the case, that's the box, that if you have a withdrawal of funds, then previously there should have been a PIN entered, so the enter PIN action should have occurred. So you would like that every trace that you see, every sequence of events that you see, that should be true. And then correctness would reduce to showing that the system that you've actually described, with all the traces that are possible for it, is contained in the traces that are allowed by this property. So you're able to produce a formal description of a relationship between how your system behaves and the properties that you want. And this is the kind of thing that the proving is doing. So for example, with timing side channel analysis, one kind of threat that we would have is that secret information may leak through what are called side channels. And timing side channel analysis might be that information leaks through the timing behavior. But if we're interested in analyzing for that, then we have to model using timed traces. We have to capture that behavior. And if there is no timing side channel, then the computation of any function should be independent of any secret information that is there. So what we would require is, if you take any two traces and they have the same visible inputs, then they should take the same amount of time. So the time taken should not differ just on the basis of secret information. Otherwise, you're getting some leakage. So there we can look at pairs of system traces in order to see whether, or in order to prove that there is no timing side channel leakage of secret information. And then with respect to property checking, described that you could have interactive theorem proving, and then there are decision procedures which do automated proving. Static analysis and dynamic analysis allows particular kinds of modeling as well. So all of these are covered within CyBOK. I see so for example, dynamic analysis with runtime verification, you may have your real system and you instrument that with particular kinds of events that give you an insight into the state of the system. And then when you run the system, you can monitor in real time the events that you're seeing, so the trace, against your model specification that captures how the system ought to behave. And then in real time, you get a verdict that it is behaving correctly. So that's one example of where formal methods could be used in dynamic analysis. So I can see I'm going to have to pick up the pace. So there are four further sections. So having covered the foundations and the particular approaches, the rest of the chapter goes through looking at how they apply in these various domains. So in hardware and for cryptographic protocols, which is a particularly successful area for formal methods, in security, and software and large-scale systems, and then also for configurations. So just briefly, hardware is only briefly covered, but it's included because it has been a very strong success for formal methods and is used successfully in the semiconductor industry and design automation companies and so on. And there are particular security-specific applications where you're looking at, say, API attacks on security tokens, or, as I've already described, side channel analysis. So there are a number of success stories of the use of formal methods in hardware, and particularly with respect to security-specific applications. When we look at cryptographic protocols, this has been a success story in the sense that the modeling approach has completely changed the way that security protocols are considered compared to how they used to be considered. So you would get a typical protocol described, in this way here, where you'd have parties that are looking to communicate and send messages to each other. You would describe how those messages should be sent. There would be all sorts of questions around this that you could ask. But the protocol would be presented, and these even became incorporated into standards before the key properties of what they were looking to achieve had been formalized. So the idea of how formal methods approach these was to use an attacker model. So instead of just looking at the messages that are passing, we look at what an attacker can do. This was introduced nearly 40 years ago, this particular kind of attacker model, where you assume the attacker controls the network and the messages that are passing around, and can interfere in all sorts of different ways. So we don't look for particular attacks, we just look for particular capabilities that the attacker has. And then we look at the whole system with the interacting parties in the context of the attacker, and see whether the parties get the guarantees that they're looking for. Model checkers have been used to do formal proofs of these kind of protocols, and theorem provers have also been used. And there's many real world protocols that matter that have now had a formal analysis on these kind of had a formal analysis using these kind of tools. So a verification would prove that all traces of a protocol would meet a required property. For example, authentication, or secure and private communication, or payment protocols have been analysed in this way, and the way that hardware security modules are used within systems have been analysed in this way. So many protocols that matter have been through this kind of verification. If I move on to software and large-scale systems, so where we're looking at software, we're looking at code. One of the things that we'd be concerned about in security is information flow, and the control of information, where we may have confidentiality, may have secret information, and public information. So, for example, if we have we don't want any of the high-level secure information to be revealed in any of what's visible at a low level. So you worry about information flowing from one level to another within a system. So there's a lot of work that's gone into the application of looking at the semantics of such programs to show that you don't get information flow from high level to low level, for example. So that's one area. It's been used in the development of cryptographic libraries, where there's a number of challenging problems that have been addressed to some extent by applying formal methods. So we talked about memory safety and heard about memory safety earlier in the day, and cryptographic security, and I've already mentioned side channels. All of these things in the development of cryptographic libraries have benefited from the application of formal methods and are growing. And there's a number of approaches that again are introduced with lots of references in the chapter. And similarly, another kind of poster child for formal methods is the Cell4 microkernel, that's a secure microkernel, which has got a number of security properties that have been formally verified. So, for example, data separation, where you have different processes, you want to make sure that you can't get interference and they can't read each other's data, for example, and also temporal separation, that resources that are left from one process are not picked up and observed by another process. So you get very strong separation of different processes, and that also means that if one process is compromised, then that won't damage other processes because of this separation. So these kind of properties have been proven to be present in CEL4, and it's been fully verified from an abstract specification of these properties right down to the implementation. So finally, I'll just have one slide on configurations and then stop. So the chapter finishes by looking at where formal methods have been used for configuration management. So configuration control is challenging because there's so much detail in there, and when you set up your particular configuration rules, you want to know, do these give me particular kind of properties? So they can be used to analyze configurations against particular properties, or even to synthesize, to translate a policy into a particular kind of configuration. So that's the final section in the chapter that's covered. So essentially, it's giving you a very much whistle-stop tour of what's covered in the chapter, and I will stop there.